Hello, everybody. I am back, and we are going to do the second section of Chapter 7, which is going to be graphing simple rational functions with one learning target, that being that you can graph rational functions. Okay, and we are going to go over the different types of problems that you're going to see on your assignments, and then the ones, if we were to assess, that would be most likely to be seen on such thing. Okay, so let's kind of get the basics of what a rational expression is. Okay, so if you looked at the previous section 7.1 when we talked about inverse variation, we saw that we were dividing by a variable, and you're going to see that same pattern is going to be happening throughout this chapter. We're going to be dividing by just a variable or an expression that involves a variable and the different variety of ways that we can simplify it. Today we're just going to see what those graphs kind of look like and the relationship between the x variables and the y variables. So the parent function, okay, so the parent function of a rational function, where we have an expression on top and an expression on bottom, okay, is the inverse variation a over x, okay, and the graph of this function when a is 1 is shown below, okay, and that's going to be the parent function, okay, so right here, the graph of the parent function f of x is 1 divided by x, and it creates a hyperbola, okay, which consists of two symmetrical parts called branches, and the domain and range are all non-zero real numbers, and we're going to explore that a little bit more. Okay, so let's go ahead and take a look at the parent function and what it looks like. Okay, so I'm going to take this and I'm just going to say y is equal to 1 divided by x, because that's the parent function. Okay, so the parent function, as you can see, is this red line here. Okay, and so let's talk about the domain and the range, because it says that you can use, like, the domain, for example, is all real non-zero numbers. So that means it's all the real numbers except for the number 0. Let's talk about y not 0. Let's look at x is 0, which is this vertical y-axis. That's where x is 0. Okay, so if you look at the function here and we were to plug in this x here that I have highlighted with 0, that would cause us to divide by 0, which gives us an error. So it creates this gap in the function or in the graph that just doesn't exist. It's not there. And let's see what happens. So as you get closer to x equals 0, the line here just keeps getting closer to x is 0. And it keeps getting closer and closer and closer and closer. And actually, you know what? We could go way off into, it looks like it's the same line at this point, right? When we're in 100 or 135. But as we zoom in and zoom in, you find out that it's not really there. So what it's going to do is it's going to get infinitely closer to that x value that creates a hole in my graph, but it never actually touches. And that is exactly what we call an asymptote. So it's creating an asymptote at x is equal to 0. That's why the domain is all real x values except for 0. Well, the same thing happens horizontally with the y values. So let's take a look at this function again. Okay, so we're looking at that and we're asking ourselves now, what x value can I plug in? What x value can I plug in that will make my y value equal to 0? Well, what number can I divide 1 by and get 0 out? Well, that creates kind of a problem because there is no number. So vertically, we have a gap in our graph because we can't divide by 0. And then horizontally, there's going to be a gap in our graph as well because you can't divide and get 0 unless this top number is 0. So same thing happens. As I zoom in, you see I'm infinitely getting closer to 0. I'm getting closer to 0, but yet it never actually touches. So that's why the domain is x is the x and y values cannot be 0. Okay, so let's go back and take a look at our paper here now that we've kind of talked about that. All right, and so, we know we're going to have a vertical asymptote at x is 0 and a horizontal asymptote at x is 0 for the parent function. That's important to note. And so any function of the form here, so any rational function has asymptotes, okay? And then the domain and range is the same as this, okay? So let's go ahead and compare g of x is equal to 4 divided by x to this function here. Okay, normally we would do this on paper, but I think we can just use the technology just fine. Okay, so let's go ahead and take a look here, and let's just compare. Let's go y is equal to 4 divided by x. Okay, so now we're looking at the difference between the blue and the red function. So you may have noticed that this number increased, and as it increased, this number stretched away from where my horizontal and vertical asymptotes cross. And that is true. So we could even decrease this number to less than 1, and we're going to see it shrink towards where those parts create, right? That's 0.5. This is 10. It's going to stretch it away. So that's all it's going to do is stretch it away. Okay? But the asymptotes are the same. They're still approaching those same things because we're still in the same general form. What if I do something like this? Let's go plus 1. Okay, plus 1. Okay, so what this is going to do is this is going to move that horizontal and vertical asymptote up 1 unit. Okay, so now instead of my asymptote approaching y is 0, it's going to be approaching y is 1. We can see this is my 1 value here, and I'm just going to be getting closer to it. It just moves it up 1. Similarly, if we were to put minus 1, what do you think would happen? It would move it down 1. Okay, so now instead of approaching 0 here, it's going to approach negative 1 here. It's going to get closer to negative 1. Okay, and this is very consistent with how we have talked about the graphs of basically any other function, in that it is going to be shifting vertically with this number out here. Okay, so what about if we put plus 1 on the bottom of that function? Okay, again, this is consistent with absolute value functions, quadratic functions, basically any kind of function that we've done is, you know, within this part, if we put plus 1, it's actually, even though it seems like it would move it to the right one, it's actually moving it to the left one. So this is changing where my vertical asymptote's at. So it was previously at x is equal to 0, now it's at x is equal to negative 1. Because if you think about it, negative 1 in for x here would cause me to divide by 0. So as I move up and move up and move up, you can see I'm getting closer to x is equal to negative 1. I'm going to get closer and closer, but I'm never actually going to approach it. Okay, so this bottom part is going to shift it left and right. Okay, similarly, if I were to put minus 1, it's going to shift it to the right. Because if I plug in positive 1 here, it's going to cause me to divide by 0. That creates a hole in my graph. Okay, so here's 1. And again, we can see that approach to 1. All right, so that's just a quick exploration of the vertical and horizontal asymptotes. So now we can go ahead and go into the actual problems that we're going to be doing. And using Desmos, which we just did there, we are actually going to graph some of these problems here. Okay. So normally, like I said, we would fill this out and then we would kind of talk about that same type of thing. But, you know, with the use of technology, we can just skip right on past this. All right. Same here. Okay, so basically the translations of the rational functions is you need to be able to draw your x asymptotes and your y asymptotes. Okay, so here's my x asymptotes, here's my y asymptotes. Okay, and then you just need to plot approximately 3. It doesn't have to be exactly 3 points, but approximately 3. We'll talk about how to get those things. And then just kind of connect your branches. Okay, again, this value, this here, is going to... it's going to move it left or right. And then this value here is going to move it up or down. Okay, and we're going to see that happen here when we actually graph, which is about to happen right now. Okay, so let's graph this function and then find the domain and range. Okay, so I'm looking at this and I'm looking at this bottom part and I'm seeing x plus 2. So in my head, based on our little exploration previously, that's kind of informing me. I already know what's going to happen there. I know that this is going to be moved to the left 2. Okay, and then this minus 1 is going to shift it down 1. Okay, that actually helps me find the domain and range. Okay, let's talk about the domain. Specifically, we know that the bottom can't be 0. So x plus 2 cannot be equal to 0. So when I do a little bit of work here, I can just solve for x by subtracting 2. And so now I know x cannot be equal to negative 2. Okay, now that's very, very good, valuable information, because what that did is it's not only helping me find the domain, but it's also helping me find an asymptote. Okay, and so as we do this, we can actually graph that. So let's find x is equal to negative 2. So negative 1, negative 2. And now I have my vertical asymptote. This is the first place that I'm going to have a gap in my graph. My graph will infinitely approach negative 2, but it will never touch negative 2. Okay, and so this informs me on my domain. I know my domain is the set of x values such that x cannot be equal to negative 2. Okay, so that's how you find the domain, and that's how you find the vertical asymptotes. They play a role that is in sync with each other. They play off of each other directly. Okay, so let's go ahead and find the range. Okay, as we talked about, standard is range. You'll never be able to get equal to 0. Well, this thing shifts the whole graph down 1. So this is now the new value that my y values are never going to be equal to. Okay, and so now I know that my y is not going to be equal to negative 1. And so then I can put my second spot that is going to be a gap in my graph. Okay, so there is my vertical and horizontal asymptote, and then now I can draw my range. Okay, my range is the set of y values such that y cannot be equal to negative 1. So I can get all real y values out of my graph as long as y isn't equal to negative 1. That's what that's saying. Okay, so now we actually have to start the actual graph of the function. Okay, this is required. I need to see this. Okay, so I need to see this line here, and I need to see this line here, as well as the domain and range when you're doing these problems independently. Okay, so what we can do now is we can go ahead and jump to the Desmos. Okay, and I will also show you in a later example how to use the graphing calculator as well, because I know some of you have access to that, though not all. So I'm trying to be provide multiple ways for you to graph these using technology. Okay, so let's go ahead and graph this function. So our function was y is equal to negative 4 divided by x plus 2. And then outside, make sure you are outside of this. So hit an arrow key to move out. We're going to subtract 1. Okay, as you can see, normally it is split right around the origin, but it clearly has been shifted to the left too, and then also down 1. We can kind of see that's that barrier. Okay, so now what we need to do is we just need to find ordered pairs. Okay, ordered pairs that works. Okay, if you want to, you can go ahead and just kind of find all the nice neat ones that intersect here just by kind of clicking on it. I'm totally fine with that. I have no personal issues with that. Otherwise, you can go ahead and hit on this little gear, and then you can get a table of inputs and outputs. It only gives you 5, but what we can do is we can start working through. So this is a fantastic sign that when x is negative 2, that our function is undefined. Because if you look at our work, we found in the domain that there's a hole at negative 2. So that's a good sign that I'm doing pretty solid work. Okay, so let's get the first ordered pair. So we have negative 1, negative 5. Okay, so we can go ahead and put that on our table that's on our graph. Okay, negative 1, negative 5. Okay, and then we have 0, -3, and then 2, -2. Okay, so now if we wanted to, we could just hit 3, and then 4, then 5, then 6, then 7, then 8, then 9, and we get all these decimals. Folks, as far as I'm concerned, I'm not concerned about getting all of these weird wonky numbers on our graph. Just snipe the whole number ones that are going to be easiest for you to graph, okay? So don't worry about getting all like 10 points. Just get all the nice, neat whole numbers. If that's less than 3, it's okay. Don't worry about it. If it's more than 3, I would like to see all of those. Okay, so now we only have one side. If you look here, we only have one side, this branch here. We can still get ordered pairs on this branch as well. Okay, so we need to start moving to the left of -2, which this doesn't have. Okay, so we can start by typing -3. Okay, when x is -3, y is 3. And then we can do -4, which is 1. Okay, and then we can do -5, which is 0.3 repeated. Again, we don't need that one, so I'm not even going to include it on my table. And then we can do -6, which is 0. I have about 3 points on each side. That seems adequate. Let's go ahead and see if there's more. -7, no. -8, no. -9, no. And -10, no. Okay, so it looks like we can switch back to our paper now. All right, so as you can see, I just kept track of the ordered pairs that we were using that we got off of the Desmos, okay? And so we can just start graphing these. Ready? Actually, before I begin, there's one common mistake that I really want to make you all aware of because I've seen this before and I really, really do not want you all making the same mistake. When I'm graphing -1, -5, it's very common to start seeing people start from here as if this is the origin. It's not the origin. You're going to graph ordered pairs as you've been taught in all previous years, okay? This, remember, is just where our holes in our graph are. So you're going to start at the original origin. We're going to go -1 and then -5. So -1 and then -5. -1, -2, -3, -4, -5. Okay, next one is 0, 3. So 0, -1, -2, -3. And then next one looks like it will be 2, -2. 1, 2, -1, -2. Okay, and then that is basically just kind of the pattern in which my branch is going to follow, so we can just kind of sketch it out from there. Please do not cross the asymptotes because we know that we're getting closer to them, but we're never touching. Okay, so let's go ahead and do this one then. We're going to go -3, 3. So -1, -2, -3, and then 1, 2, 3. And then -4, 1, -1, -2, -3, -4, and then 1. And then lastly, -6, 0. -1, 2, 3, 4, 5, 6, and then 0. Okay, and that's the graph. So we have the graph, we have the table, and then we have our domain and range. That's kind of all the major pieces that I need to see. So this problem's done. I'm pretty content with what we have here. Okay, so when you're doing these, I am expecting to see the domain and the range. I'm expecting to see the vertical and horizontal asymptote drawn on your paper. It doesn't have to be in a different color. I'm just doing that so you have a visual cue to work from. Okay, so what I think is best for you all now is to pause the video, okay, move on down to letter B, okay, and let's attempt this one on your own. Okay, so at this point, I'm assuming that you've already tried the video. You've already paused the video and you've already tried this problem. Okay, so now I'm going to walk through it so you can check your work. Okay, so I'm seeing x minus 1. That tells me my graph has been shifted to the right one. Okay, so that helps me inform of my domain. Okay, my domain, because I know that x minus 1 cannot be equal to 0. Therefore, when I add 1 to each side, x cannot be equal to 1. Okay, so there's my first asymptote. It's that x is equal to positive 1. So let's find positive 1. It's right here. All right. All right, and so then finally that means my domain is officially, if we're going to put it in set notation, x. The domain is the set of x values, so I can use all my x values such that, or so long as, x is not equal to 1. Okay, let's do the range. Okay, the range, again, it's this value here, because normally I can't be equal to 0, but I'm shifting it up 5, so now I can't be equal to 5. So y is not going to be equal to 5. Okay, so this is going to be the set. Y is going to be the set of y values such that y cannot be equal to 5. Okay, so let's go ahead and find that value. 1, 2, 3, 4, 5. There's my y value of 5. Let's draw our line through it. Okay. So now let's move on to the computer so we can see the graph. Okay, so let's go ahead and type this in. We're going to go 2 divided by x minus 1. Okay, but then we're going to also add 5 to all of that. Okay, so we can zoom out. We can kind of center it a little bit so we can get a little better view. Okay, and if you want to snipe ordered pairs like 0, 3, we know is going to be one of them. And maybe right here looks like another one, maybe. Nope. Either way, this is why we have the table, so we can convert to a table. Okay, so we know at 1 we are undefined, again, which is a fantastic clue because we've identified that 1 is outside of the domain. So let's graph these order pairs, 0, 3, and then negative 1, 4. What else do we have? 1, and then we have negative 2. Let's actually continue out that direction. Let's go negative 3. Nope. Negative 4. Nope. Negative 5. No. Negative 6. No. Negative 7. Nope. Okay, so it looks like I'm only going to have about 2 points to the left of the vertical asymptote, which is, again, not the end of the world. If you really want to hit 3 points, my suggestion is find the one that's a half if you have one. So I'm looking at here and I have negative 3 and then 4.5. So that seems reasonable for us to graph. Negative 3, 4.5. Not required, but if you are picky and like your graphs to look good, I think that seems like a reasonable place to go. Okay, so to the other side of this, when we're getting bigger now, we have 2, 7. Okay, and then let's do 3. Okay, when x is 3, y is 6. And then we can do 4, 5, 6, 7, 8, 9, 10. Okay, so let's go ahead and take that half just so, because I am a little picky and I like to see a couple points on each side. So 5, 5.5. Okay, so now we can switch back to our paper. All right, and we can go ahead and try to graph these points. Okay, so first one, 0, 3. Again, go from the original origin. 0, 3, 1, 2, 3. Okay, and then negative 1, 4. Negative 1, 1, 2, 3, 4. Okay, and then negative 3, 4.5. Negative 1, negative 2, negative 3. 1, 2, 3, 4.5. Okay, and so then that is kind of our graph. Try to get through all the points, and then as you go down, try to get closer to that asymptote, but do not cross it. Okay, and so then let's do the next one. Okay, so 0, 1, 2. 1, 2, 3, 4, 5, 6, 7. All right, 3, 6. 1, 2, 3, 1, 2, 3, 4, 5, 6. And then 5, 5.5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.5. Okay, we have each asymptote. We have roughly 3 points on each side, although in this example I would have accepted 2 points on each side. And then as well as we've included our domain and range. So that's about everything we need. Okay, so if you're still having issues, the next problems, although we are going to add a little bit extra, will involve the core of this. And so hopefully you'll get a little bit more teaching on this. Otherwise, if you're having problems, make sure you just reach out to any of the teachers available to help you out with this, and I'm sure they'll give you a little bit of more support. Okay, now, ultimately, if we were in regular sessioned classes, these problems would be more or less the ones that we actually are going to assess over. Okay, and so as I look at problems like this, the big difference is as I'm looking at this, I have an expression on the top and on the bottom, okay, which is different where we just have a number over here over another one, okay? But luckily, based on stuff that we've done in Chapter 5, which I know you all remember everything from Chapter 5, we can actually divide these polynomials and then find a remainder. And then that actually will put this in a more general form that we're more comfortable with. Okay, so let's go ahead and do this. So let's just think about division before we get going. Is like if I were to divide 2 divided by 3, and I were to do long division, I would put the 3 out here and the 2 in here, and I would ask how many times does 3 fit into 2? It would be 0 times, and then I would put a decimal here. Then I would say how many times does 3 fit into 20? Okay, 3 would fit into 26 times, and I would get 18. Then I would subtract, then I would get 2 again, and then I would add a 0. I would drop it, blah, blah, blah. Repeat. As you may see, this is going to repeat itself, so we don't have to continue any further. But the moral of this story here, me explaining to this, is when I'm dividing a number 2 divided by 3, I'm pulling the 3 out and the 2 goes inside my long division. That same concept's true here, where I'm going to have x plus 1 on the outside. And so basically all I'm going to be doing is rewriting this expression by doing long division because it's easier for me to graph. So like when our graphs are in the other form that we just dealt with, this form, okay, it's easier for me to see things like where the asymptote's being translated, right? Left 2, down 1. As opposed to this one, I'm not really sure how the asymptote's being transformed because I have x variables on the top as well. So we're going to rewrite this in an equivalent form by doing long division. Okay, so when you're doing long division, you're asking yourself, you only look first term to first term. Okay, you don't have to worry about the whole thing. You really just look first term to first term. You ask yourself, what do I have to multiply this first term to become this first term? So go ahead and we'll ask the question, what do I have to multiply x by to become 3x? So you all should be thinking about that. Hopefully you've come to the conclusion that it's 3. Because 3 times x is 3x. Once you get that, you're just going to multiply 3 times x plus 1, and you're going to put it here. So 3 times x is 3x, and 3 times 1 is 3. Okay? And then what you're doing here is you're going to subtract. All right? So we're going to subtract, so the 3x's cancel each other out, which is what we want. Okay, and then here you got to be careful. This is not 5 plus 3. It's 5 minus 3. This becomes very, very, very tricky when you have a negative number here because it would be like 5 minus negative 3 or whatever. But here you just need to know positive 5 minus positive 3 is how I would read this. And I get a remainder of 2. Okay, I know that this is a remainder of 2 because this 2 here, I cannot multiply x by a nice neat number to get 2. Okay, so that means when I rewrite this, I know g of x is going to be equal to, okay, 3 plus that remainder of 2 divided by x plus 1. Or if we wanted to write this in a form that we're a little more familiar with, I can say that g of x is equal to 2 divided by x plus 1 plus 3. And now this is in the form that we just graphed the exact same way on the previous page. Okay, so that's going to allow me to find things such as the domain. Okay, so the domain here, I'm looking at this bottom here. I know my graph is going to be shifted to the left one, or I can say x plus 1 is not going to be able to be equal to 0. So x cannot be equal to -1, giving a domain the set of x values such that x cannot be equal to -1. So we can go ahead and graph that. Okay, so there's my first hole in my graph, or gap in my graph, that is going to have an asymptote on each side. Okay, let's go ahead and do the range. We know that the y value is not going to be able to be equal to this. All right, so that informs me on my range. Okay, so now if you do not have a graphing calculator, go ahead and get Desmos out and go ahead and continue to graph those as you had previously done. But if you have a graphing calculator, here I'm going to show you how you can do that as well. Honestly, it's basically the same thing as what we've done basically all semester. So hopefully you shouldn't need too much more instruction, but if you do, go ahead and pay attention to what we have here. There's just, those little subtleties that sometimes need to be brought up. Okay, as you turn your calculator on, what you're going to want to do is you're going to want to hit window, and this screen is going to come up. And you want to make sure that your x minimum is -10 and your x maximum is +10. Same with your y minimum and your y maximum. Okay, what this is doing is basically when I hit graph, we are going to be looking at the exact same window as what we have here. That's all it's doing. Okay, so after you have that, you can go ahead and hit y equals. And then we can type our equation in here, this particular equation. We're going to do 2 divided by, and then that x plus 1 needs to be put into parentheses so we know it's grouped together on the bottom part of that fraction. Okay, and then after that we can hit +3. Okay, and then after that we can hit graph. Okay, so this is what the graph is going to approximately look like, and this is a good sign because it looks like my graph is normally centered around here, but it does look like it's been moved to the left and up, which is exactly what our asymptotes are telling us. Okay, now what we can do is we can hit second graph, and it's going to give us a nice list of ordered pairs. Okay, and so let's scroll all the way to -10 because that's and we'll just work left to right. Okay, I'm even going to create my own little table here because it doesn't provide me with one. Okay, so -10. Okay, you should be asking yourself, am I going to use this ordered pair? -10, 2.7778. No, because that y value isn't a whole number. We're really looking for mostly whole numbers, sometimes halves, just to make it easier to graph. Okay, so as I scroll down, I might use -5, 2.5. So I'm just going to put it just in case. All right. And then I'm not going to use that one. This one I will use, -3.2. -2.1. Okay, -1 and then an error is actually great news for us, because where did we say the gap in our graph was going to be based on the domain? Based on the domain, we're looking at this and we're saying x can't be equal to -1 because you're going to end up dividing by 0. And that causes an error. So this is a great sign of the work we're doing by hand kind of coming together. Okay, and then we have 0.5. 1.4. And then let's get the half in there. Looks like it's 3.5. Okay. We can scroll down through and we can see that, you know, there's no more ordered pairs for us. So, okay, let's just graph these. -5, 2.5, -3, 2, 1, 2, 3, 1, 2, -2, 1, -1, -2, and then 1. Okay, and then we can connect them with a nice smooth curve. Okay, and then next we have 0, 5, 0, 1, 2, 3, 4, 5. And then 1, 4, 1, 1, 2, 3, 4. And then 3, 1, 2, 3, 1, 2, 3.5. We can graph those. Okay. So really these problems here are the exact same as what the previous ones we have done, with the exception of, hey, we know that we might just have to do a little bit of long division if we don't have it in this nice, neat, like standard looking form. Okay, so here's a perfect opportunity for you all to pause your video, okay? And pause your video and move down to letter C and try that one on your own. All right, I'm under the assumption that you have already paused this video, you have already tried letter C, and now you're looking to see how well you did, which is exactly what you should be doing, okay? No different from in class. So let's go ahead, and it does look like I'm going to have to use some long division. So I'm going to say x minus 1, and divide it into 3x minus 2. Okay, bottom number goes on the outside, top goes on the inside, and we're going to ask, what do I have to multiply x by to become 3x? Okay, and that is 3. Okay, next you got to figure out what's going to go down here. So you're going to have to multiply 3 times x minus 1. All right, which is 3x minus 3. And then we subtract. Okay, the 3x and the 3x cancel. Here you have to be very careful. Okay, this is where I'm guessing I'm going to see most mistakes. -2 minus -3 is how this is to read, because we have minus a negative. Okay, so -2 minus -3 is going to be +1, which is my remainder, which means my new function, g of x, is now 1 over x minus 1 and then plus 3. Okay, there's my new function. Let's go ahead and find the domain. Okay, it's the set of x values such that x cannot be equal to 1. Okay, I need to backtrack and show you how I got that. I know that this is shifting it to the right one, so that's +1, or we can just straight up say x minus 1 cannot be equal to 0, and when I add 1, that means x cannot be equal to 1. Range? Okay, we know that y just straight up can't be equal to 3, so that's my range. Okay, we know that the range is the set of y values such that y cannot be equal to 3. Okay, so now that I have that, I can start just finding my x and y values that I can organize into a table. And we're going to use the graphing calculator again for this particular problem. Okay, so we're going to say that this is going to be 1 divided by, in parentheses, x minus 1, and then add 3. Okay, this looks good. It does look like it's been shifted up and to the right, so let's get our ordered pairs. We're going to start at -10. Okay, I'm not going to use this one or this one. Nope, 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 nope. I might use that one, so I'm going to go -1, 2.5, 0, 2. Okay, we've hit our error, which is good because we know we have a gap in our domain there. Okay, and so then we're going to keep on going to 4. And then 3, 3.5. Okay, so this is a good example of one that we're really just not going to get a whole lot of points, which it is what it is. I mean, when you're using these division problems, you're going to get a lot of wonky numbers. So here is an appropriate set. So let's go ahead and graph our vertical asymptote. This is 1, and then y is 3. 1, 2, 3. Okay, and then let's graph our ordered pairs. -1, 1, 2.5, and then 0, 2. Okay, so this whole graph is just really going to be tight up against each asymptote, which is fine. Which is also probably the reason why we weren't able to get as many ordered pairs. It's not stretched away very far because this number is a 1. It's pretty low, so it's going to keep it nice and tight up close to those. Let's go 2, 4. 1, 2, 1, 2, 3, 4. Okay, and then 3, 3.5. 1, 2, 3, 1, 2, 3.5. Okay, so as I'm looking back through these problems here, because this one is done, I'm looking back through these problems. I mean, it's just a series of making sure you understand how the graph is transformed from the parent function. Again, the parent function is going to be perfectly symmetrical around the origin, as this one is here on page 1. Okay, but the bottom of our expression is going to shift it left and right. The bottom of our expression is going to shift it left and right. This one, -1, shifts it to the right one. Okay, and then this outside value of +3 is going to shift it up or down. Plus is up, minus is down. Okay, and that stuff helps you find the domain and the range. Alrighty, so that is going to be the end of this lesson. Go ahead and find your assignment labeled the 7-2 assignment or homework, practice, whatever you may call it, and you can go ahead and do that. And then when we're ready to move on, we will be moving on to 7.3, which is simplifying rational expressions.